So for this lesson, we're going to focus on continuity as well as limits. We've already discussed continuity briefly, but we're going to look a little bit more in depth about the three different types of continuity. Same thing with limits. We've talked about limit behavior or end behavior and limit notation. We're going to look a little bit more in depth into some other ways as well. So a function that has no holes or breaks in the graph is known as a continuous function. In general, I want to think of a continuous function as something I can draw without picking up my pen or pencil or stylus. A function is discontinuous if there's a hole or break in the graph, so I would have to pick my pen or pencil up. And there are three types of discontinuity. So the first is a jump discontinuity. So as you can see in the first graph, my graph at x equals -1 has a break. It's colored in down here, and then there is an open circle up here. They are not equal to each other. The graph is not continuous. In the second one, there's a removable discontinuity or a hole at x equals 3. So f of 3 would be undefined because I have an open circle. And then lastly, my third picture is an infinite discontinuity. This has a vertical asymptote. So we're going to see these in a bunch of different places, but jump discontinuities we're typically going to see for a piecewise function, which we've already seen. We just haven't really talked about that. And removable and infinite discontinuities we're going to see a lot for rational functions because we've already been talking about these features. We just haven't been labeling them as a removable or infinite discontinuity. So here is a rational function. We're going to talk about limit statements in a minute, but I just want to take a look at this function as a whole. So if I look here, I have a vertical asymptote at x equals 2. That would be an infinite discontinuity. And I have a hole at x equals 5, which would be a removable discontinuity. I also have zeros and horizontal asymptotes, which we could talk about, but I'm going to save that because that's not the overall goal of this video here. All right, so I'm going to zoom out so I can take a look at this picture for a minute here, as well as my questions. So the first two questions, A and B, are asking for the limit as x approaches -infinity and positive infinity. So whenever you're looking for x to approach positive or negative infinity, those are your end behaviors. And I can determine that in a polynomial graph, a log graph, an exponential graph, any type of function, I can talk about the end behavior. And for rational functions and polynomial functions specifically, it's when it approaches positive or negative infinity. And for a rational function, when it approaches positive or negative infinity, I'm referring to my horizontal asymptote. And my horizontal asymptote is occurring here at y equals 1. So those are the same as my end behaviors. So for A and B, it is going to be at 1. The others that I'm looking at are all going to be limits at a specific number. So if I take a look here, C, D, E, these are asking about as I approach 2. And you're going to see 3 different notations. C says as I approach 2, and then it has a negative up top. D says as I approach 2 with a positive up top. And E is as I approach 2 with nothing there. So when there is a negative up top, that means it's coming from the negative side or from the left. And when I have this positive up top, that means I'm approaching from the positive side or from the right. And when there's nothing there, that's asking about the limit overall. So as I approach from the left and the right, do my hands meet? Do my fingers meet if I trace my graph? So if C and D are equal, then E is the same. If C and D are not equal, E would be does not exist. And you're going to see what that looks like as we do this. So our first one that we're looking at is the 0.2, or the value of x equals 2. X equals 2 is a vertical asymptote. We already talked about that. So as I approach 2 from the left, take a look at what's happening to this graph. It's going down. So as I approach 2 from the left, my graph is going to approach negative infinity. And as I approach 2 from the right, my graph is going up. So it's going to approach positive infinity. So since these two values are not the same, my answer for E is DNE, or does not exist. F of 2 is when I am evaluating. So I want to know when x equals 2, what is the y value? And I have a vertical asymptote, so here my y value is undefined. There is a vertical asymptote at x equals 2, and my function is discontinuous. We're going to take a look at the same thing for the next one, but this time I'm going to be examining 5 from the left, from the right, and 5 overall. So let me scroll back up. As I approach 5 from the left, I come down this way, I'm approaching what y value? I am approaching 2. And as I approach 5 from the right, as I get closer and closer and closer, closer and closer and closer, I am still approaching 2. The limit is a height. It's what you are approaching as a y value. Okay, so that's just something to think about. So as I approach 5 from the left and the right, since these two values are equal, that means that J is also 2. And now I want to find f of 5, which remember, x equals 5. What does y equal? Well, there's a hole there, and the hole has an open circle. Okay, so open circle at my hole means that it is undefined. So I have no output value. It's undefined. There is a hole at x equals 5. The function is discontinuous. And now the last number I want to examine is going to be -1. I'm going to take a look at -1 from the right, -1 from the left, and -1 overall. So -1 is over here. As I approach from the left and I get closer and closer and closer, it approaches 0. And as I approach from the right side, and get closer and closer and closer, I approach 0. And since these two pieces are equal, my overall limit is also 0 because they match. And now I want to find f of -1. So that means when x is -1, what is y? Here's my y value, -1, comma 0. So that means f of -1 is 0. And my function is continuous at x equals -1. You can find the limit at any value. If I go back up here, let's take a look at 3. If I wanted to find the limit as x approaches 3 for f of x, because you're not always going to get like the 3 pieces, the left-hand side, the right-hand side, and the overall limit. You need to know. So if I want to take a look at x equals 3, here's x equals 3, okay? And I want to know, as I approach from the left, as I approach from the right, am I approaching the same value? So as I approach from the left, I get to here. As I approach from the right, I get to there. So it meets. So at x equals +3, my limit is 4. Okay? And like I said, you can do this with any value. I could do it with x equals 1. If I wanted to find the limit as x approaches 1 for f of x. So x equals 1 is here. As I approach from the left, I end up here. As I approach from the right, I end up there. So the limit as x approaches 1 is -2 because my left-hand limit equals my right-hand limit. And we're going to take a look at a lot more of these in class.